Thanks, Steve. Thanks so much, Steve. It's a pleasure to be with you all today. Is it hot enough for you? Oh, yeah. I got a fan up here. I'm a little bit cooler, but not a whole lot. But speaking of hot, the moon is hot again, finally, after almost 50 years. And we are going back to the moon. The president and the vice president have announced that we're going to be taking human astronauts back to the moon, including the first woman to step foot on the moon as part of that expedition in the year 2024. So today it's really appropriate to talk about two things. One is to just look back a little bit for inspiration about the wonderful accomplishments from Apollo setting that stage. But it was 50 years ago. It was a different time and different reasons for going to the moon. So looking back is good, but I also want to spend most of the time today looking forward to what we're going to do next, going forward to the moon, and some of the things that we're going to do that are exciting and new and different that weren't even conceivable during the time of Apollo nearly 50 years ago. So let's start off by indeed looking back. So a little over 60 years ago, we had, or about 60 years ago now, we had the first suborbital flight by Alan Shepard in 1961. And President Kennedy declared just a few weeks after that suborbital flight, went to the Congress and said, we're going to go to the moon. Man, was that bold and audacious thing to do, because we had none of the technology at that point that really would enable such a very sophisticated, very technologically challenging mission. And he declared that we're going to go to the moon and get humans there and back by the end of the decade. About a year later, he went to Rice University in Texas and gave what many historians judge as probably the best and most famous speech on space policy, talking a little bit more about the return to the moon. So, Kent, if we could play.
But why, some say, the moon? Why choose this as our goal? And they may well ask, why climb the highest mountain? Why, 35 years ago, fly the Atlantic? Why does Rice play Texas? We choose to go to the moon. We choose to go to the moon. We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone, and one we intend to win, and the others too.
We propose to go to the moon not because it is easy, but because it is hard. That wonderful Boston accent that President Kennedy had. But it is hard. It is very hard. It was hard. It was really hard in 1961. It's still hard today. Space is difficult. It's challenging. It's dangerous, but less so. We have 50 years more of technology since Apollo that allows a greater involvement of individual companies and other countries in the space program and going to the moon specifically. But what's interesting is Kennedy was superb at crafting language to talk about those higher level goals of why America explores space. But we know from historians the real reason that Kennedy wanted to go to the moon was to beat the old Soviet Union. We had been embarrassed twice. Once in 1957 with the launch of the first satellite, Sputnik, by the Soviet Union, and were beaten a second time in 1961 by Yuri Gagarin, who was the first man in space beating Alan Shepard by months. Kennedy looked at the situation and he said that setting a really bold and audacious goal, a goal, frankly, that would require a huge investment of resources, is one that he thought we could win. And the reason, in part, was we could outspend the old Soviet Union. The Soviet Union was really right on the edge of what it was able to accomplish with its space program, and even in those days, that was recognized. So we've outspent the Soviet Union twice in history. Once was Apollo, and being successfully able to get to the moon first. The second was under Ronald Reagan's presidency, in which we outspent the Russians on military, and ultimately the old Soviet Union collapsed economically by the end of the 1980s. But the problem with setting the goal to go to the moon, and really the rationale for that being geopolitical and semi-related to, that beating the Russians, is, if you live by the sword, you die by the sword. So what happened is, when that was successful in 1969 with Apollo 11 landing on the moon, we really accomplished the goal. Richard Nixon, who was president then, at that point in time, looked at the situation, saw the amount of money that was being spent on Apollo, and in those days, we were spending up to 5% of the entire federal budget on NASA. Today, it's 0.4%, so an order of magnitude less. He looked at that. He also looked at, a few years later with Apollo 13, where we were just able to barely recover astronauts after an explosion, the famous Tom Hanks movie that many of you have seen, reenacting that and getting them back. NASA became very nervous. The administration became very nervous about there being a further accident during Apollo, and especially during a presidential election year. So for a lot of reasons, Nixon canceled the Apollo program, and this is with 3 additional missions, namely Apollo 18, 19, and 20, all the hardware built, ready to fly, and he canceled it. It was just operational money in those days. But decided to instead come back, focus the space program's attention on ultimately building the space shuttle and spending, as we have the last 50 years, in Earth orbit. Finally, though, today we're ready to explore again. But the rationale, the reasons for exploring, the reasons for going to the moon need to be different. We need to, in fact, as a society and as taxpayers, because we all are paying for that, we have to ask the question, why do we explore? Why are we going back to the moon? And I think that's a fundamental question. It's one that I've posed to the National Space Council and also to NASA on a number of occasions that we need to take a look at. So this issue of why we explore in space has been written about, has been talked about for a long time. Including by Stephen Hawking. Before he passed away, for the last decade of his life, he was a passionate supporter of space exploration. He had some interesting ideas, as Hawking always did. One of the things he said was that the situation today is somewhat like Europe before Columbus's first voyage. Spreading out into space is going to completely change our future, but it won't solve immediate problems. So by that he means that eventually when we settle, for example, on Mars, maybe when we get to planetary systems around other stars in the next century or so, the difference in gravity, the difference in connection with people is probably going to change us in ways that it's hard to imagine, physiologically as well as mentally. But in the short term, it's not going to change us in the sense that the space program is not going to be a pot of gold at the end of the rainbow. We have to look at reasons and rationale for traveling in space that go beyond just, paying the bills in the next day, but thinking about, our higher goals. Exploration is something that humans have done from the very earliest stage. We left Africa originally, where humans were first came into existence and spread around the world. That, from the very beginning, seemed to encode into our DNA that we're explorers. We want to see what's beyond that next hill. But asking that question, why, there has to, I think it's important at this stage as we look at a new era of exploration to think about it. So what I want to do is, I want to use a little analogy of a management consultant named Simon Sinek, who he studies organizations, he studies businesses for the most part. And he says that businesses in general really don't know why they exist to a large extent. They are instead focused on things like the how and what of businesses. I'll claim that NASA sometimes falls into the same category. Sinek says that many organizations really don't know why they do what they do and what their purpose is. So he makes the analogy with Apple. He said that if Apple Computer were like most companies, their advertisements might sound something like this. We make great computers. They are beautifully designed and user-friendly. Want to buy one? Well, maybe. But it makes an Apple computer just sound like many other kind of products. Instead, Apple is different. A more typical advertisement for Apple might go something like this. Everything we do, we believe in challenging the status quo. We think differently. The way to challenge the status quo is by making beautifully designed, user-friendly products. We just happen to make great computers. Want to buy one? Well, apparently a lot of people do. A lot of people have bought Macs. That sounds rebellious, doesn't it? It sounds like we want you to join part of the revolution. That was one of Steve Jobs' secrets in the 80s when he was still developing the first Mac computers, is, you know, if you join us, you're going to be on the inside of this revolution and be part of what we want to do. So join with us. And we all know that folks who do own Mac computers are passionate about it, unlike the PCs, which are, generally, a good machine, but don't develop that same kind of loyalty. So what about the space program? So if the space program thought in the same way as Apple, maybe it would sound something like the following. We believe in challenging the status quo. We think differently. We thirst for knowledge on where we came from, our destiny, and if we are alone. We build beautifully designed rockets, telescopes, and tools for exploration. Want to join us in that adventure? Yes, yes, yes. Hands want to join us in this adventure? Yes. That sounds a little revolutionary. That's what NASA was like in the early days, in the early 1960s. Dr. Jack Schmidt, who will be talking a little bit later today, talks all the time about his days at NASA in the 1960s, where the average age of people in the control room, mission operations of Apollo were, what do you think? What's your guess? 35, any other guess? 26 years old. 26 years old. You know what the average age of NASA employee is today? Not quite that, but it's 56. That's a huge difference. And I don't know about you all, but certainly as I've aged, I've gotten a little more risk averse. And the agency as a whole, NASA, has also gotten more risk averse. And it's more difficult, in fact, to take some chances. Part of it is political. Part of it is what happens when there are problems or accidents, and being called up to Capitol Hill and grilled by senators and members of Congress is not particularly a pleasant thing. But NASA needs to recover some of that edge that it had in the 1960s to be able to take some chances. If we're going to explore, we're going to do some things, we need to take some measured risks. once again. SpaceX, Elon Musk's company, is doing much that same thing. They're taking some chances. They have developed rockets with reusable engines in the first stage to make space flight more affordable in the long term. That's a step in that right direction. So in thinking about why we explore, there's a number of reasons today why we explore, as I'll tell you in a few minutes, one of which is there are opportunities for new companies to develop a true space economy. There's opportunities for tourism, there's opportunities for space science, but there's also continues to be the opportunity to inspire. I know that when I was growing up, I was 16 years old when Apollo 11 launched, and all during those early stages of Mercury, Gemini, and Apollo, that's what inspired me to become a scientist, to become a space scientist. And I think the same is true today. What I find with my own students is thinking about some new and exciting goals is where we want to go. So at its whole, let's not forget that space has that opportunity to be inspirational. It needs to be part of the equation. It needs to have some of that excitement, like NASA needs to be advertised like Apple Computer is, and be more cutting edge and be rebellious. We explore to gain knowledge, satisfy our curiosity. It's that next frontier. We've always been explorers. And so taking that leap to inspire, I think, is very important. And speaking of inspiration, I've got to show, of course, I've got to come up here and show you pictures of my grandkids, right? So Kelsey and Jackson, we took this last week. They were visiting with us for the week at the Denver Children's Museum, and there's this very nice, whoops, sorry, let me go back here. There's a very nice crescent moon here that they're sitting on, and they're explorers. I mean, you all have kids, okay? You know they're explorers just by their nature. We start off being explorers, finding out what's, you know, in the next yard over, what adventures there are in the museums. So keeping that in mind is something that we want to do. All right, so why do we explore is an important question, but also how do we explore, where do we explore, and what are the tools of exploration? Thank you very much. The bell has rung. So let's talk about that a little bit. So here's NASA's new program. I was fortunate to be part of the presidential transition team for NASA 2 years ago, in which we were asked to really look at a new direction for NASA with the then incoming administration, and to devise a plan that would be bolder, that would be one that would involve exploration, and that was part of this idea of going to the moon and then on to Mars eventually. For the last 50 years, we've been in low Earth orbit, but the moon, which is very prominent in here, which is the next step, we've got new tools for exploration, including the Space Launch System, a new very powerful rocket, about 30% more powerful than the old Saturn V, the new Orion space vehicle, which was designed and built right here in Colorado with Lockheed Martin. New landers coming from the commercial sector, robotic surface exploration, and what NASA is calling a gateway, a small space station in orbit around the moon. Many of those technologies, the hope is to feed forward to Mars, which is a lot harder to get to, frankly. The moon is only 3 days away. Mars is 9 months. When you get there, you have to stay at least a year because of the alignment between the Earth and the moon, and then 9 months to come back. So you've got to live off the land right away when you're at Mars, and very technologically challenging. And so the moon is a stepping stone in the sense that it'll get our space exploration legs back, because it's been 50 years since humans have left Earth orbit. So as I mentioned recently, the vice president in March, in fact, in late March, spoke to the Space Council, sorry, let me go back again here. And I was at that Space Council meeting and asked to talk a little bit about some of these reasons for going back to the moon and what some of the challenges were associated. But most importantly is the President announced an ambitious goal that many of us were encouraging the administration to take a look at. And that is a goal like NASA hasn't had, frankly, since the 1960s. 5 years, 2024, put humans back on the moon. Is that practical to do? The answer, I think, is yes. The reason is we've got 50 years worth of technological development now. In 1961, when Kennedy declared we were, with Apollo going to the moon for the first time, we had no landers. We had no heavy lift rockets. We didn't have the avionics. We didn't have the computers necessary to make all of that happen. The computer on board Apollo 11 had a random access memory of 4 kilobytes. What about your cell phone? Your cell phone has 5 gigabytes, 1 million times more processing power, okay? So you can imagine, that's just one example of the advancement. So utilizing that technology, bringing also public-private partnerships to the table. That is, we have a number of individual companies like SpaceX, like Blue Origin run by Jeff Bezos, who's pouring in some of their own money into these programs, coupling up with NASA and with international partnerships now makes going to the moon much more affordable and reasonable to do than was true in the 1960s. So here's the plan. I was at NASA headquarters just 2 weeks ago, and this is a new slide that was produced. The new program is called Project Artemis. Project Apollo, Project Artemis. Anybody know from Greek mythology who Artemis was? Twin sister, exactly, of Apollo, okay? And that's very appropriate because the administration has declared that one of probably 2 astronauts that will go back in 2024 will be a woman. So first female astronaut to go to the moon. I think that's very exciting and beginning to move forward in this direction. So this is Project Artemis. Artemis 1, the first launch, will be hopefully late next year, and that will be an uncrewed, so no astronauts on board, but a flyby to test out the systems for the Space Launch System, the SLS rocket, and Orion. That would be followed a couple years later by Artemis 2, so that would be crewed, but it will be an orbital mission, possibly docking at an early version of the Gateway, which is due to have a propulsion system in a first module. And then Artemis 3 in 2024, Orion will dock, the astronauts will get out, will go to a reusable lander, and then make it to the surface by 2024. At the same time, NASA, particularly the Science Mission Directorate, is working on a series of unmanned landers using commercial services. New way of doing business. NASA's buying services, not buying rockets, not buying landers, but services. So that individual companies build the rockets, build the landers, and then NASA pays to have, for example, our science payloads on board. I have 2 experiments now approved for some of the landings, both of which involve a low radio frequency telescope to go to the near side of the moon and then eventually to the far side. So that's an exciting agenda. Here is a little bit of a close-up of Artist's conception of the Orion and the, when you can see it over here. It's supposed to be a movie, but we can't get it to play here for whatever reason. So it's a massive beast. It's what's called a heavy lift vehicle that will be capable eventually of putting 130 metric tons into Earth orbit. So it's the kind of thing that has enough ability to take large amounts of mass that will get astronauts as well as landers and other payloads to the surface of the moon. So what might this look like? So let's take a look at an Artemis mission to the moon, maybe an Artemis 3. This is a video from Lockheed Martin. So here's the Orion spacecraft that we saw before in lunar orbit. So this is the beginning of the building of the gateway. This is the propulsion module that uses solar electric propulsion. That, by the way, the contract to build that was just awarded to a Colorado company, Maxar. And the famous Canadian arm, the Canadians have pledged $5 billion to work with NASA on that arm. You can see things moving a lot more quickly than they would in real time, but that gives you an illustration. And then a little look inside what this might look like in at least Lockheed's conception. It's pretty tight, it's close quarters. It's not really meant to be like the International Space Station, but astronauts could control rovers on the surface, do what we call teleoperate rovers on the surface. And here is the reusable lander that I was talking about before. So unlike Apollo, where everything is thrown away, this would have a capability of being reused. In Lockheed's design, they are in fact making reuse of the engines from Orion, as well as the module where the crew will be on top as part of the lander for their conception. Lockheed and Blue Origin both have $45 million contracts with NASA to further develop these lunar landers. And here you could have a couple of the astronauts coming back and returning to the moon. And eventually, over time, further development, other sites to visit on the moon. It's an interesting place to go. So that's the basic architecture that NASA's looking at. This is not your grandfather's Apollo, okay? This is modern spaceship with modern avionics, with 50 years with added propulsion technology that has gone into this, and new science goals that we certainly want to do. So here's another view of, a possible view of what the gateway may look like from lunar orbit. One of the things that we're excited as scientists now, if I can talk a little bit about the science that I would like to do from the moon, is the Lunar Farside. The Chinese recently landed on the far side of the moon, down in this region over here called the South Pole Aitken Basin. What you're looking at, this color image here, is a topographic map. So blue is low elevation, red and white are higher elevations. So you can see a lot of the far side of the moon is very mountainous. Up until that Chinese landing, we had never been on the far side of the moon. The reason is the moon is what we astronomers call as tidally locked. One side is always facing the Earth, that's the side we see at night, and the other side is facing away. And so in order to operate on the far side, the first thing you have to do is put a communication satellite up in orbit of the moon, which is what the Chinese did to be able to relay some of the data. We as scientists are interested in the far side of the moon because this blue region over here is called the South Pole Aitken Basin. It's the oldest, deepest, largest impact basin in the solar system. It was formed over 4 billion years ago. And it carved out a very deep into the mantle of the moon. This was a time period beginning with what's called a late heavy bombardment, a lot of asteroids, meteors hitting the moon, but they also were hitting the Earth at the same time. What's fascinating about this time period, 3.5 to 4 billion years ago, is this is when the first single-cell life began to form on the Earth. All of this bombardment was happening. That history of the bombardment, though, on the Earth is wiped out because of plate tectonics, because of the erosion, wind, water, but it's there on the moon. The nice thing about the moon is that history is preserved. It's very much like a history book. We want to get back to the moon. We want to get to this region and bring back some samples and to begin to understand in more detail what that early solar system was like. We still want to know where we came from. How did life start on this planet? And get some insight about the possibility of life maybe elsewhere. In addition, we astronomers are interested in putting low radio frequency telescopes on the far side of the moon because the moon is facing away from the Earth. It's quiet. It blocks all of the radio frequency interference coming from the Earth, which is considerable, both natural and human-made. It's the only place in the inner solar system where we can put telescopes down that operate at a few megahertz to a few tens of megahertz, so below the FM band, that will allow us to probe the very early universe, the time period when the very first stars and galaxies formed some 100 or so million years after the Big Bang. So it's a unique opportunity, the far side of the moon, to study our origins, not only the origin of the Earth-Moon system, but the origins of stars and galaxies as a whole. So you can see why, we astronomers are pretty excited by that. And here's an example of one of those low-frequency telescopes. In fact, this is brand new. This is an image that we just created this week. This is the result of a NASA-funded study I did with JPL, the Jet Propulsion Laboratory in Pasadena, to look at a design of an early array in which we have a lander, a large lander that would carry a rover and allow us to deploy our radio telescope dipoles over here. And the lander would be in contact and communication with the gateway to send our data back to the Earth. So this is a project that we're very excited about doing it. This doesn't require any astronauts, and we're able to do this all using teleoperation. All right.
The enormous feature is
a little bit more about the moon.
And it's known as the Oriental Basin.
NASA has had a probe called the Lunar Reconnaissance Orbiter in orbit of the moon for the last decade, and we've learned a lot about the moon.
Structure in the lunar crust beneath the surface, giving us a window into the geologic features of the moon's interior. Our next location receives little direct sunlight and has some of the coldest recorded temperatures in the solar system, the South Pole. The highlighted spots signify potential water ice based on temperature readings from LRO's Diviner instrument and reflectance from its laser altimeter LOLA. LOLA also allows us to peer into the darkness of Shackleton Crater by bringing us this digital elevation model. It's 21 kilometers wide and 4 kilometers deep, but it pales in comparison to the largest known impact crater in the Earth-Moon system, the South Pole Aitken Basin. Sitting on the far side, it's 2,500 kilometers across and 13 kilometers deep. We don't yet know exactly how old the basin is, but it was first seen in the 1960s by spacecraft flying around the far side. As much as we use LRO data to investigate areas we can't see from Earth, we also probe familiar territory on the lunar near side to bring back images with an all-new level of detail. This is Tycho Crater. It's around 100 million years old. Here, the Lunar Reconnaissance Orbiter camera captures the central peak with a 100-meter wide boulder at the summit, the origins of which are still a mystery. Continuing across the moon's near side, we will arrive.
So we've learned a lot about the moon as a result of some of these new probes like LRO from NASA. But also, unlike the 1960s, other countries have put orbiting spacecraft and landers. I mentioned the Chinese landing on the far side of the moon. The Indians are ready this week to also launch a spacecraft in orbit of the moon, and we'll have a lander on it to go in the South Pole, where, as you heard here a moment ago, a major discovery made within the last decade is there's water ice in these permanently shadowed craters that exist. These regions have temperatures down to 40 degrees above absolute zero, and ice has collected there over millions of years. It's a game changer as far as the moon is concerned, because once we have water, we can use that for a number of things. Of course, we can use that as water to drink, to grow plants, to break it up into oxygen and hydrogen, so the oxygen to breathe, and also to break it up into oxygen and hydrogen and reassemble it as rocket fuel, and not have to pull all of that mass from the Earth. So there's at least a half a dozen companies that have been formed now around the idea of being able to mine some of that water ice, starting off with robots and then eventually with astronauts. That's the reason that the president and the vice president and NASA has decided that that expedition in 2024 is going to go to the South Pole. It's a place we never went to with Apollo, and it's a place where there may be these precious resources that we want to be able to take advantage of. So there still is some additional technology which needs to be developed. This is, again, a new slide from NASA just showing some of the things that have to be done: precision landing, new propulsion systems, setting up some surface power systems, surface construction and mining that need to be developed. So all of those are part of the technologies and development that we think many of these will feed forward to Mars as well. So we're going to do this in part with robots, okay? Now, we've always had this interesting conception going back to, before the 1950s, classic science fiction about robots. Let me show you one such robot, one of the first one in the movies, Robbie the robot from Forbidden Planet, and I think it was like 1953.
The robot of the Forbidden Planet. Now, these are his eyes. These, his ears, tuned in all directions to receive the slightest sound. And this is his brain. Robbie, turn right. Turn left. Now back to the front. Robbie, tell me, can you speak?
Yes, Dr. Morbius.
What languages?
I am monitored, Dr. Morbius, to respond to 187 languages.
Well, I think English will be enough. Now, tell me, what are your duties here on this planet?
I clean your house. I drive your atomic car. I cook your meals.
Oh, I want that robot. He's going to cook my meals, he's going to clean my house, and drive my atomic car, which I've always wanted. So, you know, what we tended to do in the early days with robots is imagine them basically as people, and taking on personalities, having structures like that, and that's continued in more recent movies like the robots that you're all very familiar with here from Star Wars.
What mission? What are you talking about? I've just about had enough of you. Go that way. You'll be malfunctioning within a day, you nearsighted scrap pile. And don't let me catch you following me, begging for help, because you won't get it.
But here's what a real rover and robot looks like. This is K-10. This is one that we have worked with. This is at the NASA Ames Research Center in Mountain View, California. My students and I, and working with the Intelligent Robotics Group at NASA Ames, have been experimenting with having astronauts operate these rovers from space, with the idea that astronauts on board the Gateway would begin operating these on the surface and eventually, similarly, at Mars. This K-10 has multiple cameras. It has a LiDAR system for tracking. So we did the first experiment done in space about 5 years ago using astronauts aboard the International Space Station and operating the K-10 rover at the NASA Ames Research Center on a planetary body. Now, that planetary body happened to be Earth, but once again, we were able to do this without going through mission control. We went directly between the astronauts and in contact with the rover. So let me show you an example of that. So down below here, what you see is the K-10 rover. My students and I had developed a deployer for this polyimide or Kapton film, which is a bit of a backbone for a future radio telescope that we want to deploy. And up above here, you see astronaut Luca Parmentano. He's barely moving, but you can see the interface which we designed is moving, and he's operating this rover in real time. He's going around hazards, which are mapped with the LiDAR system, and also some visible wavelength images which are sent in real time. So this was the first demonstration of the operation of a rover from space. So exactly the opposite of what's usually done. What's usually done is you have mission control on the ground operating robots in space. So this is the other way around what we want to do. It was very successful. The cognitive load for the astronauts was not severe, and we feel very optimistic that this is now ready to be able to deploy in the vicinity of the moon. So this is just looking at some of the antenna material that we deployed. The rover then, in a third experiment, went back and examined its product, make sure there were no tears in the film. So overall, it was a very successful experiment, and we feel ready to go with this. So now my students in Boulder, undergraduate students in particular in Boulder, we've been working on a robotic rover and arm, mechanical arm in the laboratory. And here you're seeing a speeded up version of this. This is our little lander, and what it's doing is picking up and deploying one of the components of our radio telescope. In this case, it's just a small little monopole antenna. We're putting it down, then it comes back and picks up the power and communications. So it's a little magnetic USB that we connect to this monopole antenna. What we're trying to do with this experiment is understand the human factors, how difficult, challenging it is to do some construction on the surface of the moon by piecing together components for a radio telescope. So what you saw was a third-person view. Here is what the operators were seeing in another room when they were teleoperating this using just a game controller like what you see here, and then we collected some real data at radio frequencies that were seen there. So that's exciting. The nice thing about this is that what we're going to do in this Project Artemis, this going to the moon this time, is we're going to bring Silicon Valley to the moon with us. We're going to make a silicon moon, okay? What we're going to do is use the 50 years worth of technology, computer technology, artificial intelligence, machine learning, to utilize all of those capabilities to apply to the situation in which we're doing exploration. So unlike in 1972, when Dr. Schmidt, the sole geologist, PhD, go to the moon, doing classic field geology with his shovel, the next set of explorers are going to have a set of robotic rovers that the astronauts will be in control of. They'll be semi-autonomous. They'll be using artificial intelligence to do some of the work, but when they run into issues that are either interesting or unexplained, they'll communicate this back possibly to the face shield of the astronaut, show them a little sample of what they've seen, so that the astronaut will command a series of rovers using these advanced technological tools that weren't available in the 1960s, things of this sort. So in addition to building these simple rovers and also bringing students in, which is very important from our perspective because they're learning with real devices, building things like what we would hope to be able to put in the moon in the future, we've also been using virtual and augmented reality to begin to understand how we might do some rapid prototyping. So this shows you an example of a synthetic lunarscape that we put together. Imagine for a moment now that you've got a headset on and this is in 3D. And here's a little rover that we have put on the surface of the moon. We can activate it and move it. And again, with your headset on, you're going to feel like you're, to a certain extent, standing on the moon as part of it. This is, again, a third-person view. So we can study the mechanics of the rover. We can study the interface between the rover and the soil, the lighting conditions on the moon. The Apollo astronauts reported a lot of glare. This is the view that the rover's camera would see. So if you were an astronaut elsewhere, maybe even in the Gateway or even back on Earth, you would be able to operate it in this fashion and move it along. And this shows the two eyes that you would get. This is what, when you put those together with a headset, then is going to give you the three-dimensional feel. And then using augmented reality, these arrows, for example, show the direction we want to move in. That was a gauge showing what the fuel was. So we can use, once again, these advanced tools to train astronauts on how to operate these rovers on the surface of the moon, as well as a design tool for these in the future. So I mentioned before, commercial partnerships. That's also a game changer. That's what makes things different today than they were 50 years ago. So you have folks like Jeff Bezos. This is the lander that he introduced recently, called it Blue Moon. Sounds appropriate, right? And Bezos is pumping in $1 billion per year of Amazon stock into his company. And so working in conjunction, he's cost-sharing the development of this lander with NASA. So my plan is I want to go online and go to Amazon Prime and order the delivery of my low-frequency radio telescope on the Blue Moon in 3 days, okay? Guaranteed 3 days to the surface of the moon, okay? And then at the same time, you've got SpaceX. They're continuing to work on larger and larger rocket vehicles that will be also capable of delivering large payloads to the vicinity of the moon and eventually to Mars as well. So the difference between today and Apollo is Apollo, as we talked about at the very beginning, was not sustainable. Once those geopolitical goals were met, the justification for continuing seemed to come to an end. What we want to do is have a sustainable program. And that means there's not just one goal. There's not going, to the moon to put flags and footsteps. Yes, we want to go back to the moon, but we want to go back to the moon with partnerships with individual companies and individual countries. But we also want to go on to Mars. And so the moon is made more affordable today by these new partnerships. And instead of costing the equivalent of 5% of the national budget, a few $1 billion more will get us humans back to the moon. And then NASA can save the big bucks to take us eventually to Mars, which is really, really hard still to be able to do. So when people ask me all the time, should we go to the moon or Mars? I say no. That's the wrong question. We should go to the moon and Mars together. And then from there, there's other destinations. One of the reasons Mars is very attractive because there's a possibility of life has formed on Mars. Once Mars had oceans of water. Its atmosphere thinned, and today it's no longer able to support water, but maybe life could have formed. But that's not the only place that life could have formed in our solar system. There are also the moons of Jupiter and Saturn have oceans of water underneath their surfaces. And of course, water we know is one of the important things for life. So Europa is one of those moons. NASA is currently working on a first satellite, an orbiting mission to look at some of the water jets that are coming out from the subsurface layer and begin to probe for biogenic material. There are other possible places, Titan in orbit of Saturn, that might also be indicators. So once again, that's what forms a sustainable space program. It's not a single destination, a single reason, but a whole variety and an infrastructure, a partnership with many different players that will make space part of our everyday culture. And of course, eventually, what we'd like to be able to do, and this is much further off in the future, is to begin exploring planets outside our solar system. With the Kepler Space Telescope, we've discovered now 5,000 planets around other stars. That's pretty amazing. And with telescopes, space telescopes and ground-based telescopes, we can explore some of the characteristics of those planets and their stars. Here's a highly stylized picture of one such star that's very active, and it's flaring and producing an interaction with an Earth-like planet over here. We can use our low-frequency radio telescopes on the moon to actually probe the presence of magnetic field and some of the weather in these systems. That's one of the main reasons we want to put that radio telescope on the moon, is to study other star systems. So to summarize, I hope I've convinced you this is not your grandfather's Apollo. There's a lot of exciting new things to do. The advance in technologies that have happened in the last 50 years have opened up new and exciting possibilities. But at the same time, we utilize one of the essences of Apollo, and that is Apollo was very inspirational. The next generation of exploration should be similarly inspirational. It should drive the advances of science and technology. It should be inclusive by having individual countries, individual companies, and opening up the arms of NASA to embrace a lot of different folks from different backgrounds and cultures and ethnicities, making a new kind of space exploration, I think, that will see us advance to as a civilization. So I don't know about you, but I'm excited. I'm excited by this going forward to the moon, by what lies ahead in the next few years, in the next few decades, and I'm excited to see many of these things come to pass. So with that, I'll say thank you for your attention and happy to take some questions.